dix, neuf, huit, sept, six, cinq, quatre, trois, deux, un. Allumage volcane. 10, 9, 8. The final countdown. Spoken in French, the language of the Guiana Space Center in Kourou, French Guiana. On June 4, 1996, these words were not just a sequence of numbers. They were the crescendo of a decade-long symphony of European ambition, a testament to the continent's united push for supremacy in space. The air was thick with humidity and anticipation. This was the maiden voyage of the Ariane 5, a rocket designed to be the future. It was bigger, more powerful, and more capable than anything Europe had ever built. It represented 10 years of development, the collaboration of 12 nations, and an investment of over $7 billion. On its back, it carried the Cluster Mission 4 scientific satellites designed to study the Earth's magnetosphere in unprecedented detail. This single launch was the culmination of countless careers, a symbol of precision engineering, and the vehicle for a new era of scientific discovery. As the Vulcan engine ignited, a torrent of fire and smoke erupted from the launch pad, and the colossal machine began to ascend, slowly at first, then with gathering, undeniable force. For 36 beautiful, perfect seconds, it was a picture of triumph. The rocket climbed, piercing the tropical sky, its trajectory nominal. On the ground, in the control room, engineers watched their telemetry, their faces illuminated by the green glow of data streams. Everything was going according to plan. This was the moment of validation. The long hours, the complex calculations, the political wrangling, it was all worth it. The Ariane 5 was not just a rocket, it was a statement. A statement that Europe could compete with the American and Russian titans of space, that it could dominate the lucrative commercial satellite launch market. This rocket was designed for reliability, for power, for efficiency. And a key part of that efficiency was a philosophy well known to engineers everywhere. If it isn't broken, don't fix it. A significant portion of the software guiding this new beast was directly inherited from its smaller, time-tested, and incredibly reliable predecessor, the Ariane 4. It was a logical decision, a cost-saving measure, a testament to the confidence they had in their own proven technology. It was, in their minds, the smart thing to do. Then, at an altitude of just under 4 kilometers, 37 seconds into its flight, the dream vaporized. The rocket, traveling at nearly Mach 2, made an abrupt, violent turn. The immense aerodynamic forces, the sheer pressure of the air on its fuselage at that speed, were too much. The booster rockets sheared away from the central core, triggering the automated self-destruct sequence. The $7 billion project, the decade of work, the priceless scientific instruments, all of it vanished in a spectacular, horrifying fireball against the blue sky. In the control room, the triumphant data streams turned to static. The confident faces froze in disbelief, then contorted in confusion and despair. What had just happened? There was no warning, no indication of a failing pump or a leaking fuel line. The hardware seemed perfect. The engines were firing flawlessly. So, how did a billion-dollar project, the pinnacle of European engineering, fail so catastrophically in just 37 seconds? The answer wouldn't be found in a twisted piece of metal or a faulty engine. It was hidden deep inside the rocket's digital mind, in a single number, within a single line of recycled code that had worked perfectly hundreds of times before. This is the story of Ariane Flight 501, a cautionary tale not of mechanical failure, but of the arrogance of efficiency and the terrifying power of a single misplaced decimal point in the digital age. The ambition for the Ariane 5 was born from the success of its predecessors. The Ariane family of rockets, starting from Ariane 1-inch 1997, had established Europe as a serious player in the space race. By the 1990s, Ariane 4 had become the workhorse of the commercial satellite industry, renowned for its reliability. But the world was changing. Satellites were getting bigger, heavier. The market demanded a vehicle that could launch 2 large satellites at once, significantly reducing the cost per kilogram to orbit. The Ariane 5 was designed to meet this demand. It was a complete redesign, featuring a powerful new cryogenic main engine, the Vulcain, and 2 massive solid rocket boosters. It could lift nearly 20 metric tons to low Earth orbit, more than double the capacity of Ariane 4. This wasn't just an upgrade, it was a quantum leap. But with any massive project, budget and time are relentless pressures. The engineers at the European Space Agency, ESA, and its prime contractor, Arianespace, looked for ways to optimize development. The guidance system seemed like a perfect candidate for reuse. The Inertial Reference System, or SRI, from the Ariane 4 was a masterpiece of engineering. It had a flawless flight record. It was robust, tested, and understood. Porting its software to the Ariane 5 seemed like a brilliant shortcut, saving millions of dollars and years of development and testing. It was a decision rooted in a deep-seated trust in their own success. They believed they knew the system inside and out. That very trust, that confidence in a proven past, would become their undoing. They were about to learn, in the most public and expensive way imaginable, that in the world of complex systems, assumptions are the most dangerous form of engineering. The code they were about to reuse contained a hidden trap, a ticking time bomb set not by malice, but by the simple, unexamined march of progress. To understand how a $7 billion rocket was destroyed by a piece of software, we need to step away from the fire and smoke of the launch pad and enter the silent, logical world of computer code. The heart of the problem lay within the rocket's guidance system, specifically a component called the Inertial Reference System, or SRI, in its French acronym. You can think of the SRI as the rocket's inner ear. It's a highly sophisticated box containing laser gyroscopes and accelerometers, constantly measuring the rocket's orientation and movement. Its job is to know, at every single millisecond, precisely where the rocket is, how fast it's going, and which way it's pointing. This information is then fed to the main flight computer, which makes tiny adjustments to the engine nozzles to keep the rocket on its intended path. The Ariane 5 had 2 of these SRI units, a primary one and a hot backup, running in parallel. If the primary system failed, the backup was designed to take over instantly. This is a standard practice in aerospace engineering called redundancy, and it's meant to build a safety net against unforeseen failures. However, this safety net had a fatal, invisible hole. The software running on both SRIs was the code inherited from the Ariane 4. Within that software was a specific block of code responsible for calculating what was known as the horizontal bias, or BH. This value was part of a pre-launch alignment sequence for the Ariane 4, helping the system calibrate itself on the launch pad using the Earth's rotation as a reference. Crucially, this particular calculation served no purpose for the Ariane 5 after it had lifted off. For reasons of what engineers likely considered code simplicity or a don't touch what works philosophy, the calculation was never disabled. It continued to run in the background, a ghost of a past requirement. The problem lay in how this horizontal bias value was stored in the computer's memory. It was held in a variable defined as a 16-bit signed integer. Let's break that down. Imagine a variable is like a small box in the computer's memory, designed to hold a number. The 16-bit part specifies the size of that box. A 16-bit box is very small by modern standards. It can only hold numbers within a specific range. For a signed integer, which can be positive or negative, the range is from negative 32,767 to positive 32,767. If you try to stuff a number larger than 32,767 into this box, you get what's called an overflow. It's like a car's odometer with only 5 digits. When it reaches 99,999, the next mile doesn't show 100,000. It rolls over to 0, and the information about the 100,000-mile mark is lost. In computing, this overflow can cause the program to crash or behave in wildly unpredictable ways. Here is the fatal difference between the Ariane 4 and Ariane 5. The Ariane 5 was a fundamentally different machine. Its initial trajectory after launch was much steeper, and it achieved a higher horizontal velocity far more quickly than its predecessor. This meant that the values being generated for the horizontal bias, that now useless background calculation, grew much faster on the Ariane 5. For the first 36 seconds of the flight, the number fit comfortably within its 16-bit box. But just after the 36.5-second mark, the calculated value for the horizontal velocity ticked over 32,767. The tiny box overflowed. This overflow occurred during a specific operation. The system was attempting to take the 16-bit integer and convert it into a much larger 64-bit number format called a floating point number. This conversion is a standard procedure, but the designers had not protected this specific operation from an overflow error. When the 16-bit number became too large, the conversion failed catastrophically. The processor encountered an operand error, a fundamental mathematical impossibility it could not resolve. In the language of the system, this was a fatal exception. The software's response was immediate and brutal. It crashed. The entire SRI processor shut down. And it sent a diagnostic message to the main flight computer, a block of error data that the main computer, having never been programmed to interpret it, simply saw as garbage. Now, what about the backup system? The very reason for its existence was to save the day in a moment just like this. The primary SRI had failed. The backup should have taken over. It did. But the backup was a perfect clone of the primary system. It was running the exact same software, processing the exact same data from the same sensors, and it had performed the exact same flawed calculation. So, at the exact same millisecond, it too encountered the exact same overflow error and crashed in the exact same way. The principle of redundancy had failed spectacularly. Having two identical systems fail for the exact same design flaw is like carrying a spare key to your house, but it's a spare key for the wrong lock. It provides a feeling of security, but no actual safety. With both its primary and backup inertial reference systems now dead, the main flight computer was effectively flying blind. Worse than blind, it was being fed nonsense. The diagnostic error data from the dead SRIs was interpreted by the flight computer as valid flight data, and this data seemed to indicate that the rocket was experiencing a massive, impossible trajectory deviation. The computer thought the rocket had suddenly tilted by an extreme angle. In its logical, pre-programmed mind, there was only one course of action: correct it. The computer sent maximum deflection commands to the nozzles of the two solid rocket boosters and the main Vulcain engine, trying to steer the rocket back onto a course it was never deviating from. This created an enormous, real-world aerodynamic stress on the vehicle. The rocket was now fighting itself, its control surfaces pushing it one way while its momentum carried it another. The structural loads became unbearable. The boosters, under immense pressure, ripped away from the central core. The integrity of the vehicle was breached, and at that point, the rocket's final safety system kicked in as designed: the self-destruct mechanism. It was a final, merciful act to ensure the out-of-control vehicle didn't crash into a populated area. The billion-dollar explosion was not the failure. It was the final, logical consequence of a chain of events that started with a number that was simply too big for the box it was put in. In the immediate aftermath of the explosion, the atmosphere at the Guiana Space Center was one of profound shock and confusion. The live television feed cut away from the raining debris, but the image was seared into the minds of everyone watching. A project that was the pride of a continent had been reduced to a plume of smoke. The question, why, hung heavy in the air, a suffocating cloud of uncertainty. Before the wreckage had even cooled in the swamps of French Guiana, the European Space Agency, ESA and Ariane Space, took a critical step. They immediately formed an independent inquiry board, chaired by Professor Jacques-Louis Lyons of the French Academy of Sciences. Their mandate was simple, yet monumental: find out what went wrong, and ensure it never happens again. This wasn't just about salvaging a rocket program. It was about restoring faith in an entire continent's technological prowess. The team of investigators was a hand-picked group of Europe's top scientists and engineers. They were given full access to all data, all personnel, and all design documents. They were detectives, and their crime scene was a complex tapestry of telemetry data, software code, and engineering blueprints. Their first task was to rule out the obvious. They meticulously analyzed the performance data from the Vulcain main engine and the solid rocket boosters. The propulsion systems, they quickly determined, had performed perfectly. The telemetry showed normal pressures, temperatures, and thrust. This was not a hardware failure in the traditional sense. The rocket had not suffered a mechanical breakdown. It had been commanded to destroy itself. The focus immediately shifted from the physical machine to its digital brain. The investigators began the painstaking process of sifting through the torrent of data transmitted from the rocket in its brief 37-second life. This telemetry was the rocket's last will and testament, a stream of thousands of parameters broadcast back to Earth, tracking every aspect of the vehicle's health. Somewhere in this ocean of numbers was the clue. The breakthrough came when they focused on the data packets from the Inertial Reference System, the SRI. They saw the primary SRI shut down just after 36.6 seconds, followed instantaneously by the backup. And right before the shutdown, they isolated a specific piece of information: the diagnostic message generated by the SRI's software. They had found the murder weapon. The board now had to understand what that error message meant. They dove into the system's software specifications and the source code itself, a language called ADA. They were now looking at the exact lines of logic that the rocket's computer had executed. The digital trail led them to the conversion function, the attempt to change a 16-bit signed integer into a 64-bit floating point number. They simulated the flight, feeding the recorded trajectory data back into a replica of the SRI's software. And there it was. They watched the value for the horizontal bias climb steadily, and then, at the 37-second mark, exceed the 32,767 limit. They had recreated the crime. The overflow, the operand error, it was all there, clear as day in the simulation. They had found the bug. The discovery was a chilling aha moment. It was so simple, yet so profound. The Inquiry Board's final report, delivered just over a month after the crash, is a masterclass in technical clarity and unflinching honesty. It laid out the sequence of events without ambiguity. But it went further than just identifying the bug. It asked a more important question. How was this bug allowed to exist? The investigation turned from the code itself to the processes, culture, and assumptions that had produced it. They discovered that the part of the code containing the fatal flaw was only active for about 40 seconds after launch. Its only purpose on the Ariane 4 was to allow for a quick realignment of the system, in the rare case of a launch hold late in the countdown. For the Ariane 5, with its different pre-launch sequence, this function served no purpose whatsoever. It could have been turned off, but it was left running. Why? Because it was part of a larger software module that was deemed reliable. No one had performed a full analysis of the implications of the Ariane 5's new trajectory on this legacy code. The system's requirements, they found, did not specify what the computer should do in the event of this particular variable overflowing. The possibility was simply never considered. Furthermore, the testing procedures were flawed. The software had been tested, but never under full simulated Ariane 5 flight conditions. The engineers had tested individual components, but had not adequately tested the integrated system with the new flight parameters. The most damning finding was a failure of imagination. The engineers had reused the Ariane 4 code because it was proven, but they failed to appreciate that putting that code in a new environment, a faster, more powerful rocket, was like putting a reliable car engine into a Formula One race car. The operational conditions were so fundamentally different that the old assumptions of reliability were no longer valid. The Inquiry Board pinpointed the exact moment of failure, but their true contribution was in revealing the systemic hubris. The failure was not just a bug in the code, it was a bug in the thinking. It was the assumption that what worked yesterday would surely work today. The tiny operand error was merely the symptom of a much deeper disease, a misplaced faith in the past, and a failure to rigorously question every single assumption when building a system where the stakes are astronomically high. The explosion of Ariane Flight 501 was a public, painful, and incredibly expensive failure. It was a national embarrassment for France and a significant setback for the European Space Agency. Yet in the world of engineering, failure is often the most effective, albeit brutal, teacher. The legacy of Flight 501 is not just the story of a spectacular disaster, it's the story of how that disaster fundamentally reshaped our understanding of software reliability and changed how we build the complex, safety-critical systems that underpin our modern world. In the immediate aftermath, the path forward was not clear, but the clarity of the Inquiry Board's report provided a precise roadmap for recovery. The engineers of the Ariane program now knew their enemy. It wasn't a faulty valve or a weak weld. It was a flaw in their own process. They corrected the software bug, of course. They protected the infamous variable from overflowing and rewrote the exception handling. More importantly, they undertook a complete, top-to-bottom review of the entire flight software. Every assumption was challenged. Every line of reused code was revalidated against the specific operational conditions of the Ariane 5. Just over a year later, in October 1997, Ariane 5 Flight 502 stood on the launch pad. The atmosphere was thick with tension, a stark contrast to the confident anticipation of the maiden flight. This time, the world was watching not for a triumph, but to see if the lesson had been learned. The countdown reached 0. The Vulcan engine roared to life. The rocket ascended, and for 37 seconds, an entire continent held its breath. The rocket passed the point of failure, then continued to climb flawlessly into the heavens, delivering its payload to orbit. The success was a monumental relief and a powerful validation of the new, more rigorous process. The Ariane 5 program recovered and went on to become, like its predecessor, a dominant force in the commercial launch market, with a remarkable string of over 100 successful launches. But the true legacy of Flight 501 extends far beyond the Ariane program. The disaster became one of the most famous case studies in the history of software engineering, dissected in university classrooms and corporate boardrooms around the globe. It provided a series of powerful, unforgettable lessons. The first and most crucial lesson was about the perils of code reuse. The mantra, "If it ain't broke, don't fix it," was shown to be dangerously simplistic. The case of Ariane 5 demonstrated that code is not reusable in a vacuum. It is only reusable if its new operational environment is fully understood and tested. You cannot simply copy and paste trust. Every assumption embedded in the original code, like the maximum expected value of a variable, must be re-examined. Second, it revolutionized the understanding of system testing. It's not enough to test components in isolation. You must test the system as a whole, under conditions that are as close to the real world as possible. The failure to simulate the full trajectory of the Ariane 5 on the inherited software was a critical oversight. The disaster highlighted the need for end-to-end integration testing, where the software is subjected to the full range of data it will encounter in its operational life. Third, it forced a profound rethinking of redundancy. The failure of both the primary and backup systems simultaneously was a wake-up call. Identical redundancy protects against random hardware failures, but it offers zero protection against systemic design flaws. This led to a greater emphasis on what is called dissimilar redundancy, where backup systems may use different software, written by different teams, to avoid a single point of failure in the logic itself. Finally, and perhaps most importantly, the Ariane 5 story became a powerful argument for a culture of rigorous justification. Every single component of a safety-critical system, including every block of code, must have a clear and documented reason for being there. The fatal calculation on Ariane 5 was a relic, a piece of code left running without a valid purpose in its new context. Modern software engineering practices, especially in aerospace, automotive, and medical fields, now demand meticulous requirements tracing. An engineer must be able to point to any line of code and trace it back to a specific documented requirement. If that requirement is no longer valid, the code must be re-evaluated or removed. Every time you step onto a modern airliner, use a sophisticated medical device, or see a self-driving car navigate a complex intersection, You are benefiting from the lessons learned in that fireball over French Guiana. The $7 billion failure of Ariane 5 was a catastrophic loss, but its legacy is one of invaluable knowledge. It serves as a permanent, humbling reminder to all engineers that the systems we build are only as strong as the assumptions we make. It taught us that in the digital world, the smallest number can have the largest consequence, and that the price of hubris is paid in fire, but the wisdom gained from it can make the future infinitely safer.